It's kind of wild to think about. Some of the biggest, most powerful AI models in the world, the ones writing poetry and code, have a massive blind spot. At their core, they can't tell the difference between dog bites man and man bites dog. Today, we're going to pull back the curtain on the ingenious mathematical hack that lets them finally understand word order.
So, where does this problem even come from? Well, it's all about something called the transformer architecture. Its greatest strength is that it processes every single word in a sentence at the exact same time. This parallel processing makes it incredibly fast and powerful, but it's also its Achilles heel. Take a look at these two sentences. To you and me, the meaning is completely different, right? But to a transformer's core attention mechanism, they look exactly the same. It just sees a bag of words, a cat, a mouse, a chase. It has absolutely no idea which word came first. The whole story just evaporates. And that right there is the fundamental problem. Self-attention is order blind. It has no built-in sense of sequence, of first, second, or third. And without that, truly understanding language is impossible. So how in the world do you teach a system that sees everything at once, the very sequential concept of order? Okay, let's put on our engineer hats for a second. If you were tasked with solving this, what's the first idea that would pop into your head? Probably the most straightforward, obvious one you can think of. So let's start there. What if we just count, right? Let's just label each word with its position. The is position 1, cat is 2, chased is 3, and so on. We can just feed that number into the model along with the word itself. Seems simple? Seems logical? What could possibly go wrong? Well, as it turns out, pretty much everything. This simple idea falls apart spectacularly. First, the position numbers are unbounded. They can just keep getting bigger and bigger. A long article could have words at position 10,000, and neural networks absolutely hate huge, unpredictable numbers like that. They also prefer smooth, continuous values, not clunky integers. But the real killer? The model gets no intuitive sense of distance. It doesn't know that position 8 is closer to 9 than it is to 900. Okay, so just counting is a total dead end. We have to throw that idea out. We need a signal that's consistent, that stays within a nice, stable range, and gives the model more information. We need something a bit more elegant. We need to go back to math class. So let's build a wish list for our perfect position signal. 1, it needs to be bounded, meaning its values don't just shoot off to infinity. 2, it needs to be continuous. No sudden jumps, just smooth transitions that neural nets love. And 3, it would be great if it had a predictable, repeating pattern. What kind of function checks all those boxes? Of course, sine and cosine waves. They're perfect. By their very definition, their values are always stuck between -1 and 1, so that solves the unbounded problem. Check. And they're the poster children for smooth, continuous functions. Double check. This feels promising. But wait, there's a pretty big catch. Because waves repeat, the value for position 3 might be the exact same as the value for position 35. The model would think they're the same position, so we fixed one problem but created a new one. Our positional codes aren't unique. So a single wave isn't going to cut it. And this is where the true genius of the solution comes in. What if, instead of using just one wave, we used a whole bunch of them, all oscillating at different speeds, to create a totally unique positional fingerprint for every single word? Okay, deep breath. This is the formula from the original paper that started it all. And I know, it looks super intimidating, but I promise the actual idea behind all those symbols is incredibly clever and way more intuitive than you'd think. Let's break down what it's really doing. Really, all this formula says is this. We're going to build a long vector, or list of numbers, for each position. For the even-numbered slots in that vector, we'll use a sine wave. For the odd-numbered slots, we'll use a cosine wave. That pos is just the word's position, 1, 2, 3. And all that other stuff with I and D model, that's just a clever way to make each wave have a different frequency, or speed. That's it. So, this is the key. Positional encoding isn't one number, it's a whole vector, a list of numbers, and each pair of numbers in that list is generated by a sine and cosine wave that's oscillating at a frequency that's just a little bit different from all the others. And this is the beautiful result. This heat map shows you what those vectors look like. Each row is a different word position, and each column is one of the numbers in its vector. And you can actually see the waves. Look at the columns on the left. The colors change really fast. Those are our high-frequency waves. As you move to the right, they change much, much more slowly. Those are the low-frequency waves.
Now for my favorite analogy. Think about counting in binary. The last bit flips constantly, 0, 1, 0, 1. The next bit flips half as often. The bit after that, half as often again. This positional encoding is doing the exact same thing, but in a smooth, continuous, analog way. The fast waves are like the last bits, and the slow waves are like the first bits. It's basically binary counting for an analog world. It's just so cool. So we've created this incredible, unique vector for every position in a sentence. We're almost there. The last piece of the puzzle is, how do we actually combine this position signal with the word's meaning?
Now, you might think, let's just glue the two vectors together. That's called concatenation. But the problem is that would literally double the size of our inputs, making the model way bigger and slower to train. So the researchers went with a much cleaner, more efficient trick. They just added them together. A simple element-wise addition.
And why this whole sine and cosine setup? Well, the authors of the original paper pointed out that it has this amazing hidden property. Because of the way these waves work, there's a super simple mathematical relationship between the vector for, say, position 5 and the vector for position 10. This makes it incredibly easy for the model to learn the concept of relative distance, to understand what 5 words away actually means.
All right, let's wrap this up. This positional encoding hack is absolutely genius. It gives every single position a unique, stable signal. It avoids all the terrible problems that come with just counting. It lets the model understand not just absolute order, but the distance between words. And it does all of this without making the model any bigger. It is a perfectly elegant solution to a very tricky problem.
And that just leaves me with one final thought. At the end of the day, this massive, complex problem of word order was solved with trigonometry. Math you probably learned in high school, just applied in a really, really clever way. It really makes you wonder, doesn't it? What other simple, elegant math hacks are hiding in plain sight, secretly powering the most advanced AI in the world today?